Hi, this is a presentation of higher-order graph convolutional network with Flower-Petals Laplacians on Simplicial complex. This paper has been accepted by AAAI 2024. I will introduce this in 4 parts: background, model performance, and explanation. So higher-order interactions are everywhere in real life. This means that interactions not only between node pairs, but also between a lot of nodes. It is from the pairwise interaction to group interaction. Such higher-order interactions are common in real life. For example, in protein network, the action process of the protein is completed by a variety of proteins. In social networks, rumor spreads faster in groups. There is a Chinese verb to describe this phenomenon, which is the 3 people spreading the reports of a tiger makes you believe there is one around. In the brain network, the signal of transmission between the rumors is also the result of the joint regulation of multiple neurons. So the higher-order interaction can be represented as simplex. In mathematics, a simplex is a full connected graph. That is, a k-simplex is a complete graph with k plus 1 nodes. And a simplicial complex is a finite collection of simplexes. The boundary incidence operator describes the relationship between simplex with one order difference, and the relation can be visualized as a Hasse diagram here. Graph neural networks are famous because of its strong ability to capture the topological structures of networks. Graph convolutional networks are classical traditional graph neural network, which is able to capture the local neighbor relationships between nodes, so as to obtain the context information of nodes. So when you come to simplex, there are some higher-order graph neural networks like the MPSN and hyper graph neural network and so on. But they have some challenges. Hasse diagrams are valuable in studying simplex, but they are inherently constrained to model interactions for directly adjacent simplex and are computationally expensive to construct the multiple transitions and also required for information to pass between nodes and higher-order structures. Therefore, we design a flower-petal model which consists of one flower core and several petals, with interaction allowed only between core and petals. The target simplex are put into the flower core, and each petal contains the simplex of the same layer. Each core and petal can be unwrapped as bipartite graph. Based on the random walk dynamics on bipartite graphs, we can calculate the higher-order adjacency matrix and the Laplacian matrix, as shown in the equation here. We have proved that these two matrices are both symmetric and positive, indicating that the graph convolutional network models based on them can converge over interactions in the training process. The proposed flower-petals Laplacians of different orders capture different higher-order topological information. So we can apply different convolutional operators on each Laplacian domain to learn different patterns and integrate the learned embeddings to get a final prediction. So we propose our higher-order graph neural network, which is named Hygen. To prove the proposed model's superior expressiveness, we define a higher-order version WL test based on the random walk dynamic on top of the flower-petal model, which is proved to be more powerful than its traditional counterparts. The proposed higher-order graph neural network model can be regarded as the neural network version of higher-order WL, indicating that the Hygen is more powerful than its traditional counterparts. We show 3 non-isomorphic graphs here, which are indistinguishable by traditional WL tests, but distinguishable by higher-order WL and simplified higher-order WL with clearly complex lifting. The incorporation of the higher-order information in higher-order WL and a simplified higher-order WL enables nodes to exhibit a more extensive diversity in color compared to the WL test, consequently yielding superior performance in both node level and graph level tasks. Now we come to the experiment part. We demonstrate Hygen's outstanding performance on a range of graph tasks, including the simplicial data imputation and graph classification. Our model Hygen also achieves the optimal performance on most datasets on node classification tasks, for example like this. But we can't get the best performance in the Texas dataset. We will give an explanation later. Here, we use p-hygen to indicate the maximum order of structures that are considered. Generally, 2-hygen and 3-hygen outperform 1-hygen, suggesting that the value of higher-order information in graph learning. As we already defined higher-order models, what we really want to do is not only to achieve the higher accuracy, but also want to figure out the influence of higher-order structures. So we define the p-order strands as the sum of filter weights learned from the p-order Flower-Petal Laplacian. Let's see the trend of these 4 pictures. It can be observed that the higher-order structures decrease as the order p increase. So let's separate these graphs in 2 kinds, homogeneous and heterogeneous graphs. Adjacent nodes in homogeneous graphs tend to share the same label, while the upside holds in heterogeneous graphs. So we can see that the decreasing phenomena is more prominent in heterogeneous graph. Moreover, we observe that graphs with fewer higher-order structures tend to exhibit a weaker higher-order strength, potentially regarding the performance of hygen. For instance, in Texas, the only datasets where the performance of our model is not optimal, we note significantly weaker higher-order interactions compared to the low-order ones. The Texas has the fewest triangle among all datasets. To verify this conjecture, we manipulate the number of higher-order structures by adjusting the edge connectivity while maintaining the degree distribution as done in 1K models. The number of triangles was recorded in the upper table, ranging from -50% to +50% in steps of 10%. We found that when the number of triangles increased, the accuracy increased correspondingly. At the same time, we also visualized that the higher-order interactions strength. It can be also found that the higher-order strength shows upward trend with the increasing number of triangles. Therefore, we can get a conclusion that the accuracy ranking increases with the increasing number of triangles, and the higher-order strength increase with the increasing number of triangles. So we can see that the performance of hygen is more prominent in systems dominated by higher-order interactions. In conclusion, we propose a novel representation of higher-order networks which can easily model the interaction between different order simplex and is highly scalable. And we propose a higher-order convolutional neural network model based on this novel representation. We quantify the strengths of higher-order interactions in a data-driven manner. The expressive power of this model is proved theoretically, and the effectiveness of this model is verified by experiments. If you are interested in our research, please follow our official account, Linear's Lab and Sugarless Melon. We focus on the interdiscipline of complex network and other fields. Bye-bye.